Hi everybody, this video is about solving polynomial inequalities. Once you learn a little bit about polynomials, as in the previous video, how to factor them, how to find their x-intercepts, how to interpret their graphs, it's really easy to solve polynomial inequalities. Now when I say polynomial inequality, what I mean is, well, just that. F of x is a polynomial, and let's say we want to find all of the places where this polynomial is greater than or equal to 0. If you've already factored the polynomial, or if you've already found the x-intercepts, you've already found the zeros, because that's the same question 3 different ways, then you're done. There's actually no work to do. So let's piece all of this together. So I drew a number line that has the x-intercepts of this polynomial, and I know these are x-intercepts because we've already factored the polynomial. So just pretend you've already put in 5 or 10 minutes of work completely factoring a polynomial. So we do know how to get to this point where we know the x-intercepts. Now, there's a little bit more that we know. We know the leading term test. If you were to multiply this polynomial out, okay, the leading term would be, let's see, we have x, 2 more x's, a 4th x, so we'd have an x to the 4th power and this negative 2 in front. So the leading term would be negative 2x to the 4th. Now if we apply the leading term test and think about this function graphically, we know that as x gets large, the function values are going to be large negative numbers. So a positive number raised to the 4th power is going to be positive, but then we multiply by negative 2. And it's the same thing over here. As we go to the left, the function values will be negative. For the same reason, if x is a big negative number, raise it to the 4th power and you're positive, then multiply by negative 2 and you're negative again. So I know what the graph looks like at the two ends. What about in between? Well, let's just think about the intercepts. Now, I know that if you have multiplicity 1, as in this factor and this factor, then the graph is going to cross over the axis at this point and this point. However, this factor has a multiplicity of 2, and we know at even multiplicities the graph touches. So let's put that information together. We know the graph more or less has to look like, let's see, we got to cross over, we got to come back down, but when we hit this x-intercept, we're only going to touch, and then the graph rebounds. Of course, we have to come back down. We have to cross at this x-intercept. And there we go. The graph more or less looks like this. But that's all that I need to write the answer to the polynomial inequality that we started with. So this polynomial inequality is asking you, all right, when is this function greater than or equal to 0? So when is it positive or 0? And you can tell just by looking at this, this little chart that we made. I call it a chart rather than a graph because it's definitely not detailed enough to be a graph. So we see starting at negative 2, we have the function equal to 0, and then it's positive all the way until we get to 1, and at 1 it's equal to 0 again, and then from 1 to 3 it's positive, and then at 3 it's equal to 0. So to write the answer to this question, well, it's as simple as the function is greater than or equal to 0 on the interval from negative 2 to 3. And this is a closed interval because I do want to include the negative 2 and the 3 in the solution set because the function is equal to 0 at those 3 points. Now, if we change up the question just a little bit, maybe we'll do it like this. What if the inequality said, well, when is this function just greater than 0, strictly greater than 0? So it's almost the same answer, except we don't want to include the x-intercepts, because at the x-intercepts the function is equal to 0, and we only want to know when it's greater than 0. So here I'd have to write the answer as the open interval from negative 2, but I need to stop when we get to 1, because at 1 the function equals 0. So this is part of the solution set, and then we're going to union that with the interval from 1 to 3. So we're not including the places where the function equals 0. Now, there's a couple more inequalities that we could solve here. We might as well do those. Let's see. What about when is, I'm going to switch back to the pencil, would be a good idea. When is this function less than or equal to 0? The work is already done here in the sign chart. We just want to know the places where the function is negative, that is below the x-axis, or equal to 0. So this answer is going to look kind of odd because we have this interval from negative infinity to negative 2. We have this interval from 3 to infinity. But we also have this single point where x equals 1. Okay, because at x equals 1, the function value is 0. So that's part of our solution set to this inequality. So let's put all of this together. From negative infinity until we get to negative 2, the function is negative. And we want to include negative 2 because the function is equal to 0 there. So that's part of our solution set. And working from the left to the right, now I need to include just the single value of 1. To write that down mathematically, we're going to write that as a set, and it's the set containing just the number 1. And now we want to pick up the last interval from 3 to infinity. And we want to include the number 3 because the function does equal 0 there. So finally, I guess there's one more inequality that we could solve, and that would be when is the function negative? So it's going to be similar to this answer, but actually a little bit easier to write because the function is negative from negative infinity up to 2, and we don't want to include, negative 2. We don't want to include the negative 2 because the function is equal to 0 there, and we only want where it's negative. So I don't include the number 1 because the function is equal to 0 there, and I can skip over and go from 3 to infinity, not including the endpoint at 3 because the function is equal to 0 there. So once you've already done some work with polynomials, once you have factored them, which admittedly can take quite a while, especially if it's a high degree polynomial, you can answer these inequality questions without doing any work at all. So anyway, that's how you solve just a basic polynomial inequality. We're going to be talking about that in class in the next couple of days. See you then.